Hello my friends, and welcome back to Sky Creative Channel. Today we're diving deep into some of the most incredible construction technologies shaping our modern infrastructure. So grab your hard hat, and let's get started. Imagine building a bridge without cranes reaching every corner, without massive scaffolding cluttering the landscape. That's exactly what Freycinet accomplished on Turkey's North Marmara Highway using their ingenious push-drive method with incremental launch system. The North Marmara Highway's third bridge project features three spectacular viaducts, V17, V6, and V14, each presenting unique challenges that required Freycinet's most advanced construction technology. This isn't just any highway, it's a critical transportation artery spanning some of Turkey's most challenging terrain. NTHE V17 viaduct stretches an impressive 890 meters, while V6 and V14 each present their own engineering puzzles with varying spans and heights that would make traditional construction methods either impossible or prohibitively expensive. Here's where it gets fascinating. The push-drive method combined with the incremental launch system. Picture this. Instead of building the entire bridge in place, engineers construct the bridge deck in segments behind the abutment, then literally push the completed sections forward over the piers. NTHE magic happens with Freycinet's specialized equipment. Their hydraulic jacking system generates forces up to 3,000 tons. That's equivalent to pushing 2,000 cars simultaneously. The bridge segments, each weighing up to 180 tons, glide forward on specially designed sliding bearings coated with PTFE, the same material used in non-stick cookware, but engineered for massive structural loads. What makes this system brilliant is the continuous steel-concrete composite construction. As each 15-meter segment is pushed forward, the trailing formwork immediately begins casting the next section. It's like an assembly line, but for bridges. The technical arsenal is impressive. Freycinet deployed their proprietary launch girder system, featuring pre-stressed concrete beams with integrated steel sections. The pushing equipment includes synchronized hydraulic jacks with computer-controlled force distribution, ensuring each push is perfectly balanced. NTHE nose beam. A temporary steel structure at the front acts as the bridge's pathfinder, spanning between piers before the permanent structure arrives. This temporary nose weighs 45 tons, but reduces the maximum cantilever moment by 60%, making the entire operation possible. The result? 3 magnificent viaducts completed 40% faster than conventional methods, with minimal environmental impact and exceptional precision. This is modern engineering at its finest, where innovation meets infrastructure. South Korea has mastered something most nations only dream of, building bridges that seem to float on water. Today, we're exploring the groundbreaking sea-crossing bridge technology, developed through the collaboration between the Ministry of Knowledge Economy, NKE, and the Korea Institute for Advancement of Technology, KIAT-NIM. Building bridges over open sea isn't just about connecting 2 points. It's about conquering some of nature's most formidable challenges. Korean engineers faced extreme tidal variations up to 9 meters, seasonal typhoons with winds exceeding 200 kilometers per hour, and marine environments that can corrode steel faster than you'd believe possible. NTHE collaboration between MKE and KIAT wasn't just bureaucratic cooperation. It was a fusion of governmental vision and cutting-edge research that produced revolutionary solutions. They developed what's now considered the global standard for sea-crossing bridge construction. The breakthrough starts underwater with their revolutionary caisson foundation system. Instead of traditional pile driving that disturbs marine ecosystems, Korean engineers perfected pneumatic caisson installation. These massive concrete chambers, some reaching 50 meters in diameter, are floated to position and then sunk with millimeter precision using controlled water ballast systems. NBUT, here's the ingenious part. They developed a real-time seabed monitoring system using sonar arrays and underwater robotics. This technology maps the seafloor continuously during construction, detecting any changes in sediment or underwater currents that could affect foundation stability. It's like having underwater GPS for bridge foundations. The Korean innovation extends to materials science. They developed a proprietary high-performance concrete mix incorporating Korean volcanic ash. Yes, volcanic ash, which creates a concrete 30% more resistant to saltwater corrosion than standard marine-grade concrete. NFOR steel components, they pioneered a multi-layer coating system, zinc-rich primer, aluminum-filled barrier coat, and a fluoropolymer top coat. This isn't paint, it's armor. The system provides 75-year corrosion protection, even in the harshest marine environments. The construction sequence is choreographed like a ballet. Prefabricated deck segments, each weighing up to 3,000 tons, are transported by specialized floating cranes with dynamic positioning systems. These vessels can hold position within centimeters, despite waves and currents, allowing precision assembly of bridge segments 40 meters above the water. The result is a construction methodology that's been exported worldwide. From California's new Bay Area crossings to projects in Southeast Asia, Korean sea crossing technology is literally bridging the world's waters. Melbourne's Westgate Tunnel isn't just another infrastructure project. It's a $6.7 billion engineering symphony featuring some of the most advanced tunneling and highway construction technology ever deployed in the Southern Hemisphere. Today, we're going inside this massive undertaking that's reshaping how Australia builds its future. The Westgate Tunnel project is absolutely massive in scope. We're talking about 4 kilometers of twin tunnels under the Maribyrnong River, 2.5 kilometers of elevated roadway, and the widening of the existing Westgate Freeway to 12 lanes. But numbers only tell part of the story. This project is solving Melbourne's western traffic nightmare while connecting the city's port directly to major highways, bypassing residential areas entirely. The environmental and community benefits are enormous, removing 9,000 trucks daily from local streets while cutting travel times by up to 20 minutes during peak hours. What makes this project truly special is its integration of multiple cutting-edge technologies working in perfect harmony. From the world's largest tunnel boring machines to revolutionary noise reduction systems, every aspect showcases Australian engineering excellence, enhanced with global best practices. Meet Bella and Vida, the 2 massive tunnel boring machines that are the stars of this project. These aren't your average TBMs. Each machine is 90 meters long and weighs 4,000 tons. Imagine a 15-story building lying on its side, packed with technology. NTHE cutter head diameter is 15.6 meters, making these among the largest TBMs ever used in Australia. But size isn't everything. It's the sophisticated technology inside that's remarkable. Each machine features 57 cutting tools made from tungsten carbide, designed specifically for Melbourne's challenging ground conditions that range from soft clay to hard basalt rock. NTHE real innovation is in the automated guidance system. Using laser guidance and GPS technology, these machines can maintain their course with millimeter precision over kilometers of tunneling. The excavated material, over 3 million cubic meters total, is processed through an automated muck handling system that sorts materials for recycling and proper disposal in real time. NBUT. Here's what's really impressive. These machines don't just dig tunnels, they build them simultaneously. As the cutter head advances, automated systems install precast concrete tunnel segments, each weighing 16 tons, creating a finished tunnel structure immediately behind the cutting face. The ground conditions in Melbourne are notoriously challenging, ranging from soft marine clays to hard volcanic basalt. The project team developed a revolutionary ground conditioning system using biodegradable foam and polymer solutions that transform difficult soils into workable material for the TBM and FOR areas requiring additional support. They're using compensation grouting, a technique where grout is injected into the ground around the tunnel to pre-stress the soil and minimize surface settlement. This is crucial when tunneling under existing infrastructure like railways and major roads. NTHE project also features extensive ground freezing technology for emergency situations. If unexpected ground conditions are encountered, liquid nitrogen can freeze the surrounding soil solid within hours, allowing safe intervention and repairs. It's like having a geological emergency brake system. Above ground, the elevated highway sections showcase equally impressive technology. The project uses balanced cantilever construction for the major bridge spans, with segments cast in place using mobile formwork systems that advance automatically as each segment is completed. NTHE bridge design incorporates seismic isolation bearings. These are essentially shock absorbers for bridges. In the event of an earthquake, these bearings allow the bridge deck to move independently of the supporting piers, preventing catastrophic failure. Each bearing can accommodate movements up to 600 millimeters in any direction. NFOR, the cable stayed sections, they're using a revolutionary stay cable system with individual strands that can be replaced without removing traffic from the bridge. The cables use high-strength, low-relaxation steel with advanced corrosion protection that's guaranteed for 120 years. NTHE construction methodology is fascinating. Precast concrete segments are delivered just in time to reduce storage needs and improve quality control. Each segment undergoes 3D scanning to verify dimensions before installation, ensuring perfect fit and finish. One of the most innovative aspects is the comprehensive noise reduction system. The tunnel ventilation includes silencers that reduce noise levels by up to 15 decibels. That's a 70% reduction in perceived noise. The elevated sections feature specialized noise barriers with micro-perforated panels that absorb sound while maintaining visual aesthetics. Air quality management is equally sophisticated. The tunnel ventilation system can completely exchange the air in the tunnels every 3 minutes with advanced filtration that removes 95% of particulates. Real-time air quality monitoring ensures safe conditions 24/7. NFOR environmental protection during construction. They've implemented a comprehensive water treatment system that processes all runoff water before discharge. This system can handle 50 million liters per day, removing sediments, oils, and chemicals to ensure zero environmental impact on local waterways. Safety and quality on this project operate at unprecedented levels. Every concrete pour is monitored with embedded sensors that track temperature, humidity, and curing progress in real time. This ensures optimal concrete strength and prevents thermal cracking. NTHE project uses extensive 3D modeling and building information modeling (BIM) technology. Every component is modeled digitally before construction, allowing identification and resolution of conflicts before they occur on site. This digital-first approach has reduced rework by over 40%. NFOR worker safety. The project features mandatory wearable technology, smart hard hats with collision avoidance systems, environmental monitoring for gas exposure, and automatic emergency response. If a worker's vital signs indicate distress or if they enter a hazardous area, emergency response is automatically initiated. NTHE tunnel boring machines include comprehensive safety systems, atmospheric monitoring for methane and carbon dioxide, emergency escape routes every 250 meters, and fire suppression systems designed specifically for underground construction environments. What sets the Westgate Tunnel apart is how all these systems work together through integrated smart technology. A central command center monitors every aspect of construction in real time, from TBM performance to concrete curing temperatures, to worker locations, and machine learning algorithms analyze this data to predict maintenance needs, optimize construction sequences, and identify potential safety hazards before they develop. This predictive approach has improved construction efficiency by 25% while maintaining the highest safety standards. NTHE project also incorporates future-ready infrastructure, fiber optic networks for autonomous vehicle communication, electric vehicle charging infrastructure, and adaptive lighting systems that adjust based on traffic conditions and weather. The Westgate Tunnel project represents the future of infrastructure construction, where advanced technology, environmental responsibility, and community benefit converge. When completed, it will serve as a model for major infrastructure projects worldwide, proving that ambitious engineering can deliver exceptional results for both communities and the environment. What do you do when you need to double the capacity of a critical tunnel that can't be shut down? If you're German engineers working on the Petersburg Tunnel, you build a new tunnel inside the existing one while traffic continues flowing overhead. Today, we're exploring the fascinating tunnel-in-tunnel method that's revolutionizing underground infrastructure expansion worldwide. The Petersburg Tunnel, a vital link in Germany's Autobahn network, faced a classic infrastructure dilemma. Built in the 1960s, this 2.3-kilometer tunnel carried traffic loads far beyond its original design capacity, creating dangerous bottlenecks and safety concerns. But shutting down the tunnel for traditional expansion would have been economically catastrophic. We're talking about 80,000 vehicles daily with no viable alternate routes. NTHE tunnel-in-tunnel method emerged as the only practical solution, but it presented unprecedented engineering challenges. How do you excavate below an active tunnel without compromising its structural integrity? How do you manage water infiltration, ground settlement, and the constant vibration from traffic overhead? These questions pushed German engineering expertise to its absolute limits. NTHE project team, led by specialized German tunneling firms in collaboration with Austria's renowned tunneling expertise, developed a methodology that's now being studied and replicated worldwide. This isn't just tunnel expansion, it's a masterclass in precision underground engineering. Success begins with understanding exactly what you're digging through. The Petersburg Tunnel traverses complex geological formations typical of German highlands, alternating layers of limestone, shale, and clay with unpredictable groundwater conditions. Advanced geological investigation used innovative techniques including forward-looking ground-penetrating radar mounted on specialized drilling equipment. This technology can detect geological changes up to 50 meters ahead of excavation, allowing real-time adjustment of excavation methods. NTHE team conducted extensive 3D geological modeling using data from over 200 investigation boreholes. Each borehole provided core samples analyzed for compressive strength, permeability, and chemical composition. This created a detailed geological roadmap showing exactly where challenging conditions could be expected. Perhaps most critically, they mapped the existing tunnel's foundation and support systems with millimeter precision using laser scanning and ground-penetrating radar. This revealed that the original tunnel's foundations extended deeper than historical records indicated, information crucial for avoiding catastrophic undermining during lower tunnel excavation. The existing tunnel's structural integrity during expansion required revolutionary analysis techniques. Engineers used finite element modeling to simulate every possible scenario, from minor ground settlement to worst-case water infiltration events. NTHE solution involved a comprehensive underpinning system using micropiles and jet grouting. Micropiles, just 200 millimeters in diameter, were drilled through the existing tunnel's foundation at precise angles to create a deep support network. These aren't ordinary piles. They're high-strength steel tubes filled with specialized grout that develops compressive strength exceeding 80 megapascals. Jet grouting created impermeable barriers around the excavation zone. This technique injects cement grout at extremely high pressure, up to 400 bars, literally cutting through soil and mixing with it to create concrete-like columns in place. The result is a watertight, load-bearing barrier that protects both the existing tunnel and the excavation area. NTHE's most innovative element was the real-time monitoring system. Over 500 sensors were installed throughout the existing tunnel structure, measuring everything from microscopic movements to stress changes in support elements. This data was fed to a central monitoring station where AI algorithms could detect potentially dangerous trends hours before they became critical. The excavation itself required completely reimagining traditional tunneling methods. Standard tunnel boring machines were impossible. The confined space and need for absolute vibration control ruled out conventional approaches. Instead, the project utilized advanced roadheader technology specifically modified for this application. These machines, manufactured by specialized German equipment makers, feature vibration damping systems that reduce excavation vibration by 90% compared to standard equipment. The cutting heads use carbide-tipped picks, arranged in spiral patterns that create smooth cutting action rather than the percussion impact of traditional methods. Excavation proceeded in carefully planned stages using the top heading and bench method. The upper section of the new tunnel was excavated first, immediately supported with steel arches and shotcrete, before proceeding with the lower bench. This sequential approach minimized ground disturbance while providing maximum structural control. End material removal presented unique challenges. Standard conveyor systems were impossible in the confined space, so the team developed a pneumatic material transfer system. Excavated material is immediately vacuumed into a pneumatic pipeline that transports it to the surface, without additional machinery or vibration in the tunnel. Perhaps most impressively, the excavation advanced 24/7, while maintaining normal traffic flow in the existing tunnel just meters above. Sound barriers and vibration isolators ensured that excavation operations produced no noticeable impact on tunnel users. Supporting the new tunnel required innovations in both materials and methods. The primary support system uses high-performance shotcrete with integrated fiber reinforcement, polypropylene, and steel fibers that prevent cracking and improve impact resistance. This shotcrete achieves compressive strength of 45 megapascals within 24 hours, allowing rapid excavation progress. End steel support arches are custom fabricated from high-strength steel with anti-corrosion coatings designed for 100-year service life. These arches are installed using specialized erection equipment that operates in the confined tunnel space with millimeter precision, and waterproofing represents perhaps the greatest technical challenge. The new tunnel lies partially below the water table, with hydrostatic pressure reaching 3 bars in some sections. The waterproofing system combines multiple technologies: crystalline concrete admixtures that self-seal minor cracks, advanced membrane systems with welded joints guaranteed watertight for 50+ years, and comprehensive drainage systems that control and manage any water infiltration. NTHE's most innovative aspect is the integrated monitoring system within the waterproofing itself. Fiber optic sensors embedded in critical waterproof membranes can detect moisture infiltration, temperature changes, or mechanical stress that might compromise waterproofing integrity. This provides early warning of potential problems decades before they become serious issues. The Petersburg Tunnel Project has established new global standards for tunnel expansion in constrained environments. The methodologies developed here are being adapted for similar projects across Europe, Asia, and North America. Key innovations include the integrated monitoring systems that provide real-time structural health assessment, advanced excavation techniques that minimize environmental impact, and construction management approaches that maintain operation of critical infrastructure during major expansion work. NTHE project has also advanced our understanding of soil structure interaction in complex underground environments. Research data from this project is informing design standards for future underground infrastructure projects worldwide. The Petersburg Tunnel expansion demonstrates that seemingly impossible engineering challenges can be solved with innovative thinking, advanced technology, and meticulous planning. This tunnel-in-tunnel method has opened new possibilities for infrastructure expansion in urban environments worldwide, proving that we can upgrade our infrastructure without disrupting the communities that depend on it.